So, what makes a physicist create a video adapter for a 1989 Game Boy? Apparently Tetris, I was told. In this talk, Sebastian will show us how he was able to create a cartridge module that actually acts as a USB video. And with that, yeah, Sebastian, take it away. I want to see this.
Yeah. Yeah, thank you very much for the introduction, and thank you everybody for giving me this stage. That's incredible. Let me quickly explain what you're seeing here, because I brought a few live demonstrations. So what we're talking about today, the main title is Reconstructing Game Footage from the Game Boy's Memory Bus. That's quite a mouthful. The short title is the GB Interceptor, and that's a project I made, an open source project that we're talking about, which does exactly what the main title says. What you're seeing here on camera is actually a heavily modded Game Boy, but this would also work with the original Game Boy from my childhood, and it's pretty much the same like my childhood, because my parents always imposed a 1 hour limit of playing to me, so again have this 1 hour limit. Feels just like coming back to my childhood. But the reason I'm showing you everything on this thing is because that has been modded with a modern display instead of this original thing, which would be quite hard to see for everybody. But everything I'm showing works with an original Game Boy. It actually has an original mainboard inside. Okay? Then the device we're talking about, let me also quickly show you, often is depicted like this. This is just the same thing I have here, but only with a 3D printed case. That's perfect. And the idea is now that anybody who wants to record or stream something from their original Game Boy, their unmodified Game Boy, of course, can have this adapter in between and record from it without modifying the original hardware and maybe the beloved Game Boy they know from their childhood. It's not in the frame, so I just plugged in Tetris. Okay, and it's actually not working when I'm showing it. Oh yeah, I just unplugged it, right? So, sorry. Let's reconnect this. Yeah, there we go. No, it's not working. Great. Usually it works, otherwise I wouldn't be here. Okay, so while this is trying to work again, let me explain why I'm doing this. Okay, yeah, now it's working. Okay, so if you're somewhat familiar with how retro gaming works today, you would know that, of course, we've got emulators we could play on to stream stuff and record stuff. There's something called the GB operator, which is somewhat an emulator that can read the cartridge, which coincidentally has the same letters chosen, not related to any trademark. Yeah. And there are, of course, modern Game Boy clones like the Analog Pocket. Some people might have heard of that one. And, of course, there are HDMI mods that you can apply to an original Game Boy. And I added the GB Interceptor to this list, and the quick reason is that someone contacted me about Tetris, so yeah, that part was correct in the introduction, because they wanted to do a Tetris tournament, and everybody brought their own Game Boy on which they trained. They wanted to keep their muscle memory working on the original device, and you cannot ask everyone to mod their Game Boy just for streaming. So he asked me about it, and I came up with this. And to be honest, I haven't streamed anything yet, except for this talk now. For me, of course, it's just curiosity and figuring out how to make this work, and it was a lot of fun, I tell you. So let me explain how this is even possible before we look into the details. An important part for this, if you're thinking about, oh, why couldn't I do this with a PlayStation as well, or something like, okay, that one has an HDMI out, right? But important part for this is that the Game Boy does not cache anything, so it directly reads from the ROM, so the game cartridge is just external memory. It also can read from this ROM in the cartridge as fast as it can read from its internal RAM, which means that there is no reason for any Game Boy game to load the code into RAM first before executing it. You only have to do this if you want to modify the code on the fly. So most of the time, the code is directly executed from the cartridge. Yeah, this is the problem they mentioned. So I tried to talk louder. The Game Boy will simply execute most of the code directly from the ROM, and The entire bus, the memory bus, is simply a shared bus between the cartridge and internal memory. Not entirely, so there is a DMA operation which would split things, and for most internal parts we cannot see the data that's transferred, but we can see the address that the Game Boy is requesting data from or writing to, which is also quite helpful. And so this means that most of the time we can simply look at the bus and see exactly what the CPU is doing at that moment or which instructions it's receiving. So in this talk, let me quickly give you an overview of the hardware of the GB Interceptor and then look into 3 details, how we recreate the memory in there, emulate the graphics unit of the Game Boy, and then finally something that's more modern topic but makes this device so simple to use for everybody, MJPEG encoding on a microcontroller. So we start, of course, with the cartridge. Yeah? So okay. So actually, I had this on my disk drive from a YouTube video I made about this. So, but there will be stuff specific for today. So if we look at the 32 pins of the cartridge, first of all, there's a power supply for the cartridge, or voltage supply, which is not relevant to us. The GB Interceptor is running off USB power, but this helps us to determine whether the Game Boy is on or off, simply to give some message for the user. The more important part are these 4 pins, specifically the clock pin. This gives us just a latch every time something is written to the memory or read from the memory. So it's a 1 megahertz bus, so 1 million times per second. We get an edge here, which tells us we're writing or reading, and the other 2 pins tell us whether it's a read or a write. Chip select simply helps to the cartridge to tell that, yeah, it's whatever is happening right now is none of its business. Okay, so simply to ignore something. And then we have 16 pins making up the address. It's a 16-bit address. Yeah, so this can address up to 64 kilobytes. And finally, there are 8 pins for the data. So simply imagine 1 million times per second, there is an edge on the clock signal, and then at the moment this edge comes, these 16 pins have to be set by the Game Boy, which give it an address, and depending on whether it's reading or writing, the cartridge has to set these 8 pins, or the Game Boy has to set these 8 pins. Now, to actually connect our microcontroller to it, I designed this PCB, which is, first of all, as I mentioned, open source. Yeah, so design and yeah. It's maybe noteworthy that this is actually open enough, and I intentionally chose it, that everyone who wants to have one can buy it on AliExpress by someone who's absolutely not related to me, and I don't earn a cent from it, but it becomes quite cheap to get one of these this way. Okay. But more importantly, the PCB then has this edge over here, which looks just like the pins from the cartridge, because that end goes into the Game Boy. And over here, these points where I can solder something onto it is where I have to solder the cartridge slot. That's something you can easily buy. It's an aftermarket part, and you can simply solder it on. On this image, it should be, well, it's the unassembled PCB. And those 2 are electrically connected directly without anything in between. So that's important. Even if I do not plug in the interceptor, or even if I took a screwdriver and pulled off the microcontroller, the Game Boy would still be able to to play the game. So there's nothing interfering with the game. It's just as original as it gets. So to be honest, the name GB Interceptor is a little misleading. It's not intercepting anything. So the better name would probably be GB Eavesdropper. But I think you agree that this sounds less cool. So yeah, I went with GB Interceptor. So the only interesting part about this entire PCB is that I added a few bus transceivers that allow me to also hook up the signal from the data bus to an RP2040. To those who are not familiar with the term RP2040, that's the microcontroller from Raspberry Pi. It's not a Raspberry Pi, for those who haven't heard about Raspberry Pi Pico. So a Raspberry Pi usually is a single board computer with an operating system and everything. That's not what's in here. The Raspberry Pi Foundation also released the Raspberry Pi Pico, which is an actual microcontroller. And the RP2040 is the microcontroller on board of the Raspberry Pi Pico. And to those who are familiar with the Raspberry Pi Pico, almost the entire design of the GB Interceptor is taken from the manuals of the Raspberry Pi Foundation. So I'm not that much of an electrical engineer. Yeah, so this is mostly a Raspberry Pi Pico, just a clone from their minimal hardware example, including the oscillator and voltage regulator and everything. And the only thing I added are these bus transceivers that allow a direct connection to the memory bus. And the reason that I picked the RP2040 can be seen in the schematics. Don't worry, you don't have to read everything right now. Yeah? So I highlight what I'm interested in, and they are these two little things here called PIO, that stands for Programmable I/O. They go in between the CPU cores and the GPIO pins. So I hooked up the memory bus to the GPIO pins. The cores could theoretically read those pins directly, but the problem with this is, since it's a 1 megahertz bus, the CPU would have to react to an interrupt 1 million times per second, or it would have to observe the clock, and that takes away a lot of cycles and is somewhat too slow. Instead, these programmable IOs can take care of that, because they are simply for state machines per programmable I/O, so in total we would have 8 state machines that are directly hooked up to the GPIO pins. And for the GB Interceptor, we only need one of these state machines. This actually only needs 4 instructions, so they are like saying little computers is maybe a bit much because they are dumb as a brick. Yeah? They only understand very few instructions. Most of them are around reading GPIO pins and pushing stuff to a queue, first in, first out queue. But that's exactly what we need. So it takes only 4 instructions for the state machine to observe the clock from the cartridge bus, and then read out all 32 pins every time there is a clock event and push it onto the queue from where the CPU can pick up each bus event whenever it's convenient. Okay, so the CPU does not have to be interrupted. It can handle each bus event at its own time, and after that pick up the next event. The only limit is that it may not fall behind more than the size of this queue, which I think is like 4 instructions. So it's not that much, but it can even out a few tight spots. So that's pretty much the entire GB Interceptor. And so now the rest is software, and we have 3 tasks that I have to talk about now. The first core of the RP2040 now has to interpret these bus events that were picked up from the programmable I/O and recreate the video RAM of the Game Boy. Because, I will show this on pretty much in 3 slides, then there's this part of memory in the Game Boy which entirely determines what's shown on screen, and we have to get a copy of that. We cannot see this directly on a bus. We can see the addresses that the Game Boy tries to read from or write to in this VRAM, but we cannot see its content. We have to recreate it by following the instructions to the CPU that we can see on the bus. Then the second core has to emulate, and that's really just pure emulation, emulate this graphics unit on a Game Boy that's called Picture Processing Unit, or short PPU. I will use that term several times, to render the image based on that state of VRAM. And then the remaining sources, and we have to talk about what is remaining after that, have to handle MJPEG encoding and act as a USB video class. Because that's the nice thing about this device in the end from the point of view of most retro gaming enthusiasts, because this can simply be plugged into most systems without the need for any drivers, because it really acts like a video camera. Yeah? So let me quickly demonstrate, because you can quite literally use it as a video camera. So some of you might have seen this thing. That's the Game Boy camera. It's one of the first digital cameras out there, and certainly the first one I ever owned. It's also one from my childhood. It goes in the other way around, because the GB Interceptor shows the other direction. And if I turn this on, oh, it's pointing at you, but don't worry, there's privacy built in. The resolution is so low. So yeah, you can pretty much plug this into any Linux system, Windows system, Mac OS, and actually also Android, and simply go into shoot mode of the Game Boy camera, and you, it's down here, sorry, and you can simply, you're still seeing me, right? So it's maybe a little bit too late after the pandemic when everyone was doing video conferences, but if we have another video conference, that's the way to go. So yeah, and as I said, it works perfectly with everything I tried under Linux, Windows, and macOS. On Android, the only limit is that it's an external webcam. Android supports external webcams, but most of the apps don't. Most apps only think of the internal cameras. So it's a little bit difficult to find a decent app that supports this, but this is not a driver issue, but simply that nobody usually cares about external webcams on a mobile phone. Yeah. Okay, so now on to the three things that I mentioned that we have to talk about. The recreating VRAM from the bus events, the PPU emulation, and MJPEG encoding. So yeah, I have to start with a little bit of theory, but I keep it as little as possible. Because the internal memory of the, or actually the memory bus of the Game Boy addresses pretty much everything mapped onto the 16-bit addresses. So the lower half of these 16-bit addresses goes directly to the ROM. So this would be something external. That's something that goes through the GB Interceptor. That's something we can see. Also, some games implement external RAM, which then would also be visible to our little device here. But then there are things like the video RAM. That's the part that we are after. That's not visible because that's an internal part. We can still see the addresses that are addressed, yeah, but we do not see the data. Same goes for the working RAM, and there's something called the object attribute memory. That's a little piece of 160 byte that determines the location of the sprites on screen. So this is also important to recreate the image that's shown on screen. So yeah, I'm aware of that, and I need this also, but during this talk, when I refer to VRAM, I usually mean both the VRAM and this little 160-byte piece at the end that's also required to draw something on screen. Then it might be worth mentioning that the I/O is also an internal part. So if I press a button that's not visible on the GB Interceptor, that's an internal part where the addresses are also mapped onto a specific register where the Game Boy can read out which button has been pressed, as well as a link cable. And yeah, there will be a slide about this problem. Yeah, and so what we need to do is we need to observe what the CPU is doing, and then for this upper half of the memory, maybe this one is not required, but it's also in there as well, we keep a local copy of the memory on the RP2040. So while we see instructions for the Game Boy, if the Game Boy receives an instruction, write this value into this part of video RAM, then we simply mimic this instruction and write the same value into our copy of video RAM. That's the basic idea. In terms of instructions, so we have a 16-bit memory address, but an 8-bit CPU. These are the opcodes of the Game Boy CPU. And yeah, don't worry, I will not drag you through a bunch of assembly today, yeah, but just to give you an idea what this looks like. This is the beginning of what the GB Interceptor sees when you start The Legend of Zelda: Link's Awakening. Game Boy games always start at the address 100, but they almost immediately jump to a higher address because there's something else in the way there. And so what we need to do is we have to observe the first bit of data, look up the opcode, that's trivial one, that's no operation, nothing's happening here. Look at the next one, C3, so C3 would be, oops, over here. That's a jump. And now there's the tricky part I want to show you. This instruction takes 3 bytes to be explained to the CPU, but the CPU takes 4 cycles to execute it, which means that after the C3, we see 2 bytes that are part of the instruction. That's the jump address where the CPU should jump to, what should be executed next. So this is the opcode. This is the data. And then we see a 4th byte because the CPU takes 1 more cycle to execute the jump, but the memory bus does not stop there. Yeah, there's still something happening. You can see from the address that the Game Boy is actually masking it outside of the ROM space so that very simple games do not react to it. But besides that, we simply have to ignore that because that's just junk that's happening on the bus while the CPU is still busy. It's not always junk. For those who are a little bit more into these kind of systems, here you can see the stack pointer being addressed. Yeah, but I don't want to go into these details, but most of the time it can simply be ignored. So for every game and everything we do, we have to understand which parts are the opcodes, which parts are data, and what is junk that can be ignored. And luckily, we do not have to do any decisions on our own. So if the Game Boy decides to do that jump, we do not have to emulate the program counter, so which address comes next. We simply see it. The Game Boy is dragging us through the game, and every branching, every decision is done by the Game Boy. So we cannot actually do a wrong decision. Yeah, we can only display something wrong on the screen, which we will see later, but any branching, any if, happens on the Game Boy, and we simply see the result. Only problem with this is that these conditional jumps are a bit trickier, because if we look up this made-up example, for the address 20, that's a conditional jump if the 0 flag is not zero, is not set. Typically a comparison of a value. Yeah, and you see here it takes 2 bytes because the second byte. So this is the opcode. This is the second byte. This means that we jump 5 bytes ahead. So that's quite trivial. But the problem is, if we look at 20, there it takes 3 or 2 cycles. And this depends on whether the jump has been taken or not. And to determine this, we still have to observe the address, because otherwise we wouldn't even need the address, because we could simply follow the opcodes that are coming in. But we need the address to see, okay, here the address has been incremented by once, so the jump was not taken, and this is the next instruction, increment of register B, doesn't matter. Or in this case, the jump was taken because the address did not increment, but the Game Boy nicely put the higher bit up to get it out of ROM space. And so this is garbage that we need to ignore. So just as an example of a few of the details that you have to look into when you try to execute the code that's seen on the bus. So I hope at this point the idea is clear what we're doing. Intentionally, I wanted to show a bunch of edge cases, but I realized that I'm showing a bunch of assembly to you, and that I only have 45 minutes or 50 minutes, something about that. Let me just show you a few of the tricky bits and then mention the others. One problem can be that the data, as I mentioned before, from the I/O registers is not visible to the GB Interceptor. And one example for this is the diff registers. The divider register is pretty much a fast counter. It's simply counting up all the time. And that's used by many games for random number generation. So imagine this counter is counting up all the time. And at some point in the game, the player presses start, and then that random number or sequence of numbers that comes from there is used to generate a random level. And the problem is that's not visible. 90% of the times that's no problem, because that number is then used internally by the game for a jump or conditional jump. Why is it not working again? It has stage fright, has it? That's a little bit embarrassing if I want to tell you how easy it is to use this device. So. Come on, that looks better. So, yeah. I can show you what I mean with the random numbers. I think most of you are probably familiar with Tetris. If you're not familiar with it, you should really try it. It's great. So let me just start a game. So this is a typical example of random data being generated. That's called the garbage stack. So in this game mode, you have to remove these lines that have been generated randomly. And if you look closely, you see, okay, the layout matches up. That's because the random numbers are used for a branch at some point where the where you. So the random numbers are used to trigger a branch to decide whether there's a gap. I think it's because there are multiple numbers mapped to gaps, so there's a jump, and the GB Interceptor just executes the code that's responsible for a gap. But the design of the garbage blocks is actually just an offset calculated from the random number, and we do not know this offset because that's just an arithmetic operation. And if you look, for example, at the bottom left block here, this one has a different design than that one. And that's true for pretty much everyone here. So actually Tetris, for which I designed this, has examples of where it doesn't work that well, because it cannot see the random numbers generated, or the clock signal that's used for random numbers that's created internally. And unfortunately, the Tetris also has the worst case example as well. because the link cable, so serial transfer register, is also part of the I/O registers. So if you go into a two-player match of Tetris and use the link cable with the second Game Boy, if you've ever done that, you might know that if you see Mario, then you were the one who started the game. So this is the controlling Game Boy for the match. And if you see Luigi, who's unfortunately always second place, then you are on the second Game Boy. And what's happening if you start, if your Game Boy is the controlling one, then your Game Boy generates the garbage stack. And just like in the example before, you cannot see it here, but you've seen it in the previous example, you have got the same layout visible on the interceptor, but the designs differ. So that's not that bad. That's okay. We can deal with that. But if you're the second player, then what happens is the first Game Boy generates the garbage stack because it should be the same for both Game Boys. And then those Game Boys become quite lazy because the first Game Boy simply transfers the entire data that goes into VRAM and into work RAM through the link cable, and the second Game Boy writes it just into its memory without doing any branching or any checking on it. Which means that to the GB Interceptor, nothing's visible there, and the zeros you see is simply just the default value of the memory at this point. So that's an example of where it really doesn't work. But trust me, at the end I will show you some statistics of how many games are working. That's an exception. And as I mentioned, the same is true for the gamepad input. So if you press a button, the interceptor has no idea that you press that button. But the trick is that in, again, most cases, the games simply read out the joypad register, do a conditional jump if button A has been pressed, then execute the code that makes Mario jump. And so we have no idea if that button was pressed, but we simply follow the code that makes Mario jump because that's being executed. So in most cases, it doesn't matter. There are some few examples where, again, a bit for the direction is used to flip sprites on screen to mirror the player when he's moving. I'm not sure why they do this. I don't think that it's much faster this way because they're doing conditional jump anyway to accelerate the player, but luckily that can then be fixed with game-specific fixes, which I will mention or show later again. I just mentioned them, I will show them later. Other tricky bits, which I just mentioned, interrupt detection. Game Boy also has interrupts that can occur at certain times, and that can be tricky. Code execution from RAM still occurs sometimes for various reasons. That's not as tricky because we already created a copy of that RAM, and the code in RAM has to have come from somewhere, and that's something we have seen. Really tricky is DMA transfers. The Game Boy has one specific DMA mechanism to copy data to OEM memory, and if that happens, then the memory bus actually splits and we cannot see the addresses anymore. So there's a DMA unit that can, for example, transfer data from the cartridge, and in that moment we see this transfer, not what the CPU is doing. But most of the time the games luckily do not do anything significant, so most of the time it's not much of a problem. That's actually a part where I found a bug in a Game Boy game, which I wanted to show you. It's in the abstract, sorry, I figured I don't have the time for that. You can ask me later about it. And of course, many little edge cases. But besides those, that's the point where we have a copy of the video RAM. Okay. So the next thing we have to do is graphics emulation. And for this, I first have to give you, again, a short introduction on how the graphics of the Game Boy works. If you want to learn more about the graphics, there's an amazing talk about how the Game Boy works by Michael Steil from the 33rd Chaos Communication Congress. I will give a link at the end. So that's my suggestion. So this is only a basic idea of what's happening there, because the Game Boy does not use a frame buffer like modern devices would do, where you can simply draw everything, the entire image, and then hand it over to the graphics unit to be displayed. But instead, it has to set up everything from these tiles. So this is most of the part that's in the video RAM. That's what we are after. And as you can see from the footage from Zelda here, recorded with an emulator, so we can see the tile data, the entire thing on screen is simply stamped from these tiles, from something called a tile map, which is simply a map of these addresses. Something that Zelda doesn't seem to be using at this point is also that this tile map is larger than the screen, and there's a scroll register, so you can also scroll this background map in certain ranges. And on top of that, there are some special features like a window, which is responsible for drawing this status screen down here, and of course sprites, which are called objects on the Game Boy, which are the players and the enemies on top. Okay, but it's all created from these tiles. And one other thing that you need to know, which is actually the tricky part, is that the Game Boy renders everything on screen like an old CRT. So line by line, it draws from left to right. And you now see this gray area is what I have as a screen, and then eventually it will draw everything else. And the green areas that I'm showing here is the part where, actually internally, the location of the virtual CRT beam, because the Game Boy, even the original display, didn't need to be drawn line by line. I think it's probably because everything at the time was written that way, is where it's outside the screen, virtually. Yeah? And this is important to the games, because while the PPU is drawing something, VRAM is not accessible. So in this animation, I had this little block here, so it's blocked while it's drawing the image, and then it's accessible after that. Also, for those who are familiar with this, I know this is a simplification. There are some more details in timing and how long this takes. But the important part for the games is that they have to wait for the green areas to draw something or to change anything about the graphics, or most things of the graphics. That's called horizontal blank. And that's called vertical blank. Vertical blank means there are 10 entire lines where the CPU is not interrupted by something being drawn on screen. So that's what the most easy thing for most games to change the entire screen. So you could change stuff during V blank and then draw the entire screen, change stuff during V blank. But of course, that's boring and that's quite limited. Many games will change stuff during H blank. And that's very important to us because we need to know the state of the VRAM for each line that's being drawn. Because if something in VRAM is changed to the next line, it doesn't help if we are emulating rendering this line up here. Yeah? So we need to be quite exact about the timing. And I would say there are 3 levels of what can happen there. The first one is easy. The game changes stuff in VRAM during VBlank. Pretty much what you would do nowadays. You change everything while nothing is shown on screen, and then the next frame is drawn. And the timing in which the game does this is about 1 millisecond. That's easy. I mean, you've just seen that Tetris works, so that's fine. That's not much of a problem. The level 2 is when the game changes something during H blank. And that could be changing some tiles, but also the typical example from demo scene, when you've got a logo which wobbles because it's made up of the background tiles. And the scroll register, which I just mentioned, is changed so that things do not align like this. Now it's the Game Boy who's not happy. You shouldn't do this, but come on, we all want to. Better. Okay, the example, those who are familiar with Game Boy games know that this is a game, you see people reacting to this. This game is famous for its demo scene-like effects. So this is the effect as I just meant. The game is changing the scroll register during each blank every time. So let's do this one more time. So this requires a precision of 40 to 68 microseconds. It really depends on what's on screen. That's what I meant. It's a simplification, what I had before. Come on, it's really? Okay. No, this is gone. It's not nice if this happens on stage. I mean, I've tried it so many times. Now everything is gone. That's great. And it's garbled on the Game Boy as well. Just see that I'm bending everything here, so maybe I should take a little bit more care while handling this stuff. Okay, let's try again. Although I'm not sure why the camera is gone as well, that's a bad sign. But then I just have to explain what you should see. Sorry about that. Oh, come on, I tried it so many times. Is that a good idea? Did the camera go to sleep? No. Okay. Okay, no idea. Let's simply explain what you're seeing. I think this might have gone out. That's great. Now everything is off. Okay, well, for those who are wondering how this presentation works, now it reloaded, but at that point it should trigger to reconnect to the camera. Okay, well, too bad, because the next example would be the really exciting one. But something, okay. Okay, because the next level would be that exact game, which is called Prehistoric Man. And that game, so maybe I can hold it up to the camera, but then you don't see what the interceptor makes out of it. I'm not sure if those, at least who watch the stream, can see it. What that game does is it does not only change everything during H-blank, it actually also makes changes while lines are drawn on screen. So actually during the time where the video memory cannot be changed. Yeah, maybe some of those who stream this can see it. So there's text on top of it, which changes while it's being drawn. And, oh, now okay. They just needed a pause. Okay. Okay, so let's do this again. No, I just have to figure out how to get back the time, right? So let's show it again, because then hopefully it will work now. But I hope you believe me that this was more a problem of the presentation technique of being able to stream the camera than anything. So you see, they're changing stuff while the line is being drawn. And what they're doing is they change the color palette while it's drawn. So they cannot access VRAM, but they're changing the color palette on how the tiles are mapped onto the 4 shades of gray or 4 shades of green of the Game Boy. And this means they're changing the color palette every second CPU cycle, which requires a precision of 1.9 microseconds. And as you could just see, that's something I cannot do on the GB Interceptor. I think the problem is mostly that the precision of the graphics emulation is not there, because I have to do some shortcuts to be able to do this on a microcontroller. And it's not that much of a problem of figuring out how to synchronize the thing. Yeah. Yeah, but besides that, usually timing is not that much of the problem, because we have different mechanisms. Oh yeah. If you want to learn more about Prehistoric Man, I recommend this blog entry. Sorry, I have to go on. Check the recording later if you want to see that URL. Because that game is really interesting in terms of old school graphics. So we have 3 means to determine where the game is, and it's simply looking at the mechanisms that the game uses to determine when it can write to video RAM. One mechanism is simply interrupts. The Game Boy has 2 interrupt mechanisms that are relevant for this, either interrupt on entering VBlank, or this interrupt here, this status register, allows to set a specific line when interrupt should be fired. Unfortunately, this is a little bit slower than entering a tight loop on the CPU and observing the stat register directly. So if games have to be really precise about this, they will do that. That's trickier. The GB Interceptor can recognize many loops because that register has been read, and then there's a conditional jump right after that. But yeah, this is more or less free programming that the developers can do, and there are edge cases where this does not work automatically. And for the other examples, we need game-specific fixes. Which means I hash everything that's written to video RAM, and the interceptor comes with a large library of hashes or footprints, which I created by running using an open source emulator, PyBoy was it, implementing my hashing function, and then emulating 1,600 games on my PC to set up that database to recognize games, just so that for the few games where this doesn't work, I can set up a specific address where I know the synchronization once it reaches that address. Okay, so yeah, that's pretty much all of the old school stuff, because now we have to handle, have to get this into the modern world, by doing, by creating a USB video class device. So you already see this will be MJPEG encoding. But when I created this, I did not even think that that would be possible. I thought about extracting the data and reconstructing the game on some host software, which would have been a nightmare, because you would have to address all the operating systems, explain Windows users how to install Python distribution and stuff like that. Yeah, so instead, I eventually noticed, okay, TinyUSB, the library that most RP2040 projects use, supports a video class device. Only problem is, since I designed this beforehand, I'm stuck with the onboard controller, which is only USB 1.1, so what they call full speed USB, which is about 1 megabyte per second in the isochronous mode that I used at the beginning for those who are really into USB. But if you do the calculations, the Game Boy runs at 60 FPS with a gigantic resolution of 160 by 144 pixels, 2 bit per pixel, that's 4 shades of green, yeah? And we could easily fit this into the stream. Problem is, if we look into the specification for the video class, we see a bunch of compression algorithms which at that time I thought were entirely out of the question because the RP2040 already has all its hands full. So I looked into uncompressed video, and there are 4 color formats allowed, and the problem is those are actually color formats. So not 2-bit per pixel, but the best we can do would be NV12 with 12-bit per pixel. The problem here is that we've got an 8-bit grayscale image, which is already much more than we need. And on top of that, there's a 2 times super sampled color or luma channel, chroma channel on top of this, which is additional 4-bit per pixels. And if you do the math, the first version of the GB Interceptor could only do 29 frames per second. Now, the Europeans in the audience would say, okay, that's fine, 25 frames per second were always fine, but the problem is that the Game Boy does these 60 frames per second internally. And that's a problem because it uses this for some of the effects. So if we look at a game here that, let me just tilt this up shortly, that's called Bubble Bobble. Not sure if anyone heard of the, okay, you know this. I have to admit, I didn't know it beforehand. Yeah? So I use this as an example because it uses a lot of transparency effects which require this refresh rate. So we have to look at the story. It's probably awesome. But you find the same effect, for example, also in The Legend of Zelda and in many other games. Because the Game Boy, if it needs to draw transparency, it of course cannot do so with only 4 shades of gray, but you see these bubbles here are somewhat transparent. And if we look at the proper recording of this and slow it down by a factor of 10, it does so simply by turning them on and off. In this case, it's flipping both sides of the bubbles, but could also be just the entire image flashing. So on the actual screen, it looks like it's transparent because it's faster than our eyes. Actually, on the modern modded screen, you might be able to spot it if it wasn't for the camera, but on the old screen, this looked just like transparency. Problem is, if you do this with the 29 frames per second GB Interceptor, it looks like that. Yeah? So this is now real time. Problem is not only that, so it would be okay if it was 30 frames per second because the first Interceptor already was able to do what I call frame blending. It could mix 2 frames and therefore create the transparency. But with just 29 frames per second, once per second, you slip to the other half of the image, and it just looks weird or flashes once per second, and it's not nice. So yeah, the retro enthusiasts wanted 60 frames per second. So what could we do? I looked at what MJPEG would require. So let me give you a very quick introduction of what MJPEG is. MJPEG is just a sequence of JPEG images. That's really simple. There's not much more to it. And you need 5 steps to encode a JPEG image. First step is convert RGB to grayscale and color channels, luma and chroma. That's trivial because we already have a grayscale image and don't care about color. And also nicely, JPEG supports purely grayscale images, so that's good. So we can simply throw away the rest. Then you have to split the image into 8x8 blocks, which is not too difficult, but can be annoying if you have to address the pixels in different sequence on a microcontroller. On a 32-bit architecture, which encodes 4 of the pixels in 1 byte, especially. And then you need to calculate the discrete cosine transform. To my fellow physicists and mathematicians, that's similar to a Fourier transform. Quite similar, actually, and you can simply calculate the coefficients to recreate the image. To everyone else who hasn't looked into this yet, the idea is that you make up each 8x8 tile of these 64 tiles. Let me demonstrate. So I can reset this to 0. And if you, for example, mix this tile with this tile, you get some kind of a diagonal. And if you turn this one on as well, then the black part is actually negative numbers, but you can show this with colors. This cancels out the other part, and you get something like a quarter circle. And this way, if you take anything from this image, you see different superpositions of these tiles to recreate the image. Okay? It's also nice for these ones when only the horizontal ones show up, for example. Yeah? That's actually not... So the problem with this is you need to calculate these coefficients, and that's not that fast. You can use a lookup table for these tiles, that's okay, but still the calculation is much more than the capacity that I would have left on the RP2040. And by the way, for your information, this is not yet where compression kicks in. This is not lossy. So this could be perfectly reconstructed. The compression is the next step, the quantization, where you decide that the the eye is not as good at spotting imprecisions on the higher frequencies down here. And then you quantize that and accept errors here. And if you do that, then you get the typical artifacts that we all love and know from JPEG. Yeah, so that's the actually lossy part of the calculation. If you have the discrete cosine transform, that's probably not that hard as well, because yeah, it's just a quantization. But the discrete cosine transform is something where I already gave up. In the end, you also have to encode this. There are two options that are common for this type of project. It would usually be Huffman coding, which I will not explain here. So the idea is that you have a very number of bits that you can use, shorter strings of bits for more common numbers and longer parts of bits for the more rare numbers, which is also really annoying because you have to do a lot of bit shifting and bitwise manipulation to fit this into your 32-bit blocks if you really do this on a... So a PC doesn't care about this, right? But a microcontroller can be stressed out by this. So I gave up on this and I thought, okay, that's impossible. I don't have any resources left. This thing is at its limit, when someone suggested something on GitHub. So Ikatsuchi, I hope I pronounced it correctly, also known as Placed on Twitter. Someone's laughing, okay. Suggested that we could simply blow up the image by a factor of 8, and that way we could get a compression ratio of 5 bit per pixels. Okay, how would that work? Let's have a look. If we increase it by a factor of 8, we get an image that's 1280 by 1152 pixels. That's almost full HD. So not that promising, right? But let's look at what we have to do then. So converting RGB to grayscale, that's trivial. That has been trivial before. That's fine. Split image into 8 by 8 blocks. That's especially trivial now because each 8 by 8 blocks is now one of the pixels that we just rendered. And then calculating the discrete cosine transform is now also trivial, because if you look back at our little toy here, a homogeneous block is just that top left tile. That's called the DC component. The other ones are called the AC component. And here we just need to adjust the brightness, and that's our homogeneous tile. The other ones, we don't care about them. We do not have to do that calculation at all. We only have to encode this DC tile now. So that's trivial now. Quantization is especially trivial now because we only have 4 shades of gray. Actually, if we allow for frame blending, that's 7 shades of gray because of the mixes that can occur. That's still the limit of quantization that JPEG allows for. And the encoding, again, that's something I don't have time to explain now today, but he was right. His example had a different number of bits. I changed it a little bit so that we have exactly 5 bits per block. And that now means that we can encode everything with only these 2 lines that have to be executed on the CPU. Sorry, I know it's annoying to read code like that, but if you are really that quick with that line, then we probably should switch positions. But okay, the thing in JPEG is that the pixels are delta encoded. So this means the difference from the previous pixels encoded, which is the only reason that this is so complicated. Each 32-bit integer represents 4 pixels, so I have to shift them by 1 block and take the difference and take one of the pixels to the next iteration. So these 2 lines encode 4 pixels at the same time. And then they are written to the programmable IOs. And that's where all the remaining hardware of the RP2040 is used, because the rest is done by the programmable IOs and chained DMA. Even if I wasn't running out of time, I did not intend to go through all the details here. But the quick idea is the CPU uses these 2 lines to write 4 pixels each. In total, 32 pixels split to 2 state machines of the programmable I/O. And from there, the result the CPU doesn't even have to care about the result. The result is taken up by chain DMA that can be triggered by the programmable I/O. And the end of the DMA operation can trigger the next DMA. That's what makes it chained. And they can split it onto 2 more state machines each. And in the end, everything is written to block in RAM, which can directly be served to the user. So there are 1 or 2 lines that are required to trigger the final chain DMA, simply because of how they align and cannot be triggered automatically. But in the end, this means that really the CPU only has to once in a while shove a few pixels up into this pipe, and everything else simply is written to RAM by the hardware. And that's how we can achieve this. Only problem is 60 FPS fits in there, but then we look again into the specifications, and it tells us, you have to have a color channel. So we have to do 2 times subsampling, and so unfortunately there are now 2 modes for the GB Interceptor. The mode that works everywhere, which offers 30 frames per second and a mostly unused a color channel. And you can there's a button you can switch it to green if you like that, yeah. But you could also do this in post. And a mode for 60 FPS for the kind of host software that accepts JPEGs that are only grayscale, which is easy for most host software. For example, I just created a very short pull request for OBS so that the current version of OBS also accepts the 60 FPS version in all 3 operating systems. Okay, and so this way I can show you now. Come on. Again, the amazing story. Come on. But yeah, you can imagine what it will look like. So this is now the 30 FPS version with frame blending, of course. Yeah, but if you can see it, it looks just like on the screen. And this is now MJPEG encoded, which also helps with compatibility. And that's how I get to the final slide summary and some hints for further information. So summary is mostly compatibility chart. So far, as people have reported, because I don't own everything, I've got a few Game Boys here that you can try later, but it works on pretty much every Nintendo device that can run original Game Boy games, but only grayscale games, just to be sure, even if it says Game Boy Color or Game Boy Advanced. That's only if you plug in a grayscale game in there. It does not work on the analog pocket, simply because the how I detect the interrupts. There's one little difference in the timing. I think it's easy to fix. I promised it a year ago to fix it, but I'm a little bit worried to break something else if I do that. And some exotic aftermarket thing called the Game Boy Color. I don't own that. I don't know why this doesn't work. In terms of games, we've got a total, and time's up, but I'm almost done. We've got a total of almost 200 games, or more than 200 games, including hybrid games and special cartridges. Most of them work. From those reported working, there are some with minor glitches. I count Tetris among them, so if you've seen this example. And only 4 classical games and 1 special cartridge. The special cartridge, again, I don't own that. I'm not sure what's going on there, but the classical games, they are just glitching that much, I would say it's unusable. And for host software, as I said, Linux, Windows, and macOS, everything I tried worked. On Android, there's a problem that the few apps that support external cameras are not really those high-quality apps, and 2 of them worked, 1 didn't. But as I said, it should not be a driver issue because it's an MJPEG external webcam. Yeah, and with that, so as I mentioned, if you want to learn more about how the Game Boy works, I highly recommend the Ultimate Game Boy talk by Michael Steil. You find it in the media library of the CCC, of the 33rd Chaos Communication Congress. For the technical details, have a look at gbdev.io. That's a public domain repository of all the people on whose shoulders I'm standing, who learned everything about the Game Boy. So there's everything in there that you want, especially the pen docs in there. And more stuff from me. I've got a blog at There Ought to Be. Specifically, GB Interceptor can be found at There Ought to Be, a Game Boy capture cartridge. Just note, this one is before MJPEG, so it mentions the 29 frames per second limit. You can find me on Mastodon and other social media channels, but this and YouTube is the most important ones. GitHub repository over there. And since I'm running out of time, just the last announcement. You can later at 10 p.m. meet me at the House of Tea, opposite of Saal 1. And if you want to chat about anything, details of this, if you just want to touch the wooden Game Boy, that's okay as well. So I'll be there. And now, so thanks. Sorry for being a little bit long.
What?
Thank you.
What an amazing labor of love. I'm sure there are going to be questions. We have 4 microphones in the room, and we have a Signal Angel who already has a question for us. Signal Angel, go ahead.
Yes, thank you so much. First of all, the internet was very impressed with your talk. There's a ton of great feedback here. Can you clarify if the 60 FPS supports now means that you have a lossless captured result on the host machine?
Yes, except of course for the mistakes that Interceptor could do. Okay, so just this asterisk, the thing that you saw with Tetris, that the wrong tiles are shown, that of course is not fixed by this. But this MJPEG encoding, I didn't mention it. This is lossless because the DC component, the quantization is less than the individual pixels. So this is lossless. You get every single frame. There might be an exception if there is the, I'm not sure, there are some times where the screen can be turned off by the game. There might be something that's visible on the GB Interceptor that's not visible on the Game Boy. But besides those edge cases, in the regular case, you should get every single frame and lossless. The MJPEG part does not introduce any compression artifacts or anything.
Microphone 1.
Hi. Have you tried kind of backwards guessing the values that they cannot observe? For example, if you read the value that you can't observe and then take a branch based on that value, you can see the branch was taken, so you can make assumptions about that value to fix the graphic glitches.
Yes, many of the game-specific glitches work that way, but they're quite simplified because of the limited resources that I have available. So what I cannot do is, so in theory, of course, you could track of everything, keep track of many possible branches, and when a branch is taken, decide which branch was actually taken to revert it back. But I only have the simple version because resource limited, also I'm at the limit of the RAM of the RP2040 with what I'm doing, is that I simply implement specific addresses, and when code reaches that specific address, I know that a specific value was there. So for example, when I mentioned that the gamepad input is unknown and a sprite has to be flipped, I simply have a short entry in this game database, which tells the interceptor if the game reaches this specific address, then this bit has to be set, and that makes the figure on screen correct. But there's no automatic way because there are no resources left on this device. Maybe at some point I have to do a new version with a faster processor, but yeah.
All right, thank you.
So microphone 3.
Thank you for your great presentation. I have a question about not the content of your presentation, but about your presentation itself. With Magic, you have created this great PowerPoint, this great presentation, or the great slides.
Well, the tool I use to create it is called a text editor, but the way I present it is that's just a web browser. So this is an HTML page with some JavaScript, and also works on pretty much every operating system.
Thank you.
Microphone 2, please.
Have you tried cheat modules like Game Genie or Game Shark?
Yes. It looks a little bit ridiculous if you do that. So I've got one here. You want to see it, right? I don't know any codes or anything, so I cannot run it right now, but I tried it. But it starts with questioning which way it has to go in. Oh yeah, of course, you have to put in the GB Interceptor close to the Game Boy because it needs to see what goes through this thing and not what if the Game Genie changes after the GB Interceptor has seen it, it doesn't work. Which then means this goes on the wrong way, and then in the end, this has to go this way, I think, because it was always wrong in the Game Genie. And yeah, so I do not recommend this, yeah, but it works. I tried it. Yeah. Oh, so, and I will remove it now because I'm mechanically worried about my Game Boy.
So microphone 1.
Hi, very amazing talk. Thank you very much. But Sebastian, what about audio?
Yeah, I should have expected that. I have to admit, in the first version, I ruled out audio simply because I was happy that I could even achieve that, and I thought that anyone who wants to stream or record this can simply plug in something to the audio jack. So that's a simple solution, of course. But I've been thinking about it, and I think it's not that tricky if you don't want to have a perfect representation, because this chained DMA, which I didn't know when I started the project, can be quite useful to jump in lookup tables to, for example, reproduce sign functions, stuff like that. So maybe a few things can be done, but at the moment with the MJPEG encoding, I'm also using up many of these additional resources, so I think there just is not more room in there. I have it on my to-do list to at least look into it, but I don't think that there's much I can still squeeze out of it. So until then, I think there's one Game Boy Advance which does not support this, but for everyone else, sorry, it's the old school audio jack.
Thank you.
So we're starting to run out of time for Q&A. Microphone 1 again, very briefly.
Hi, awesome talk, thanks. So what's the video latency minus what the USB host is doing?
Sorry, I don't have the number in my head. I once made a Q&A video where I tried it with the old version with NV12, and it was better than expected, but something I wouldn't play on. I have to admit I don't have the number now. I should check it with the MJPEG version because it became quite low, but probably nothing for true retro enthusiasts who prefer FPGA systems over emulators. So if that's the question is aiming at that, I can play while watching the screen, but I think of those who really master action, fast action games would not be happy with it.
Okay, thanks.
Microphone 4.
Thank you. Has this kind of video streaming out of the RP2040 also been tried for other video formats? Are you aware of any such projects?
Not that I know of. Also, I'm not sure. So I got the suggestion from this guy on GitHub, so that's why I referred to him. I could not really find if something like this has been done before, but you also have to remember that this is, of course, very specific to the Game Boy, to this specific image that we have on the Game Boy. You cannot throw this technique on any kind of image that you want to encode. So this is quite limited to grayscale, this high quantization. And of course, if you want to encode a larger image like that, remember that the host has to deal with the image that has been scaled by a factor of 8. That's fine for the small image, but if you try to encode a full HD image this way, maybe the microcontroller can keep up with it because it's a simple task for it, but the host software will blow it up by a factor of 8 and probably run out of memory that was reserved for this before it can do anything with it. So I'm not sure if this can be transferred to too many projects, but I would love to see it, and I'm not sure if somebody has done something similar before.
Well, even cooler if you're the first one.
So with that, I think we're out of time and we're out of questions, which is an amazing coincidence. Let me, well, help me by thanking Sebastian for this amazing talk and effort.
Thank you.